We will see the procedure for numerical implementation of level set based topology optimization. So for the level set based topology optimization, for evolving the level sets, we solve the Hamilton-Jacobi equation. So that is given here, dou psi by dou t equal to minus v times mod del psi minus omega g. So the last term omega g accounts for the nucleation of new holes, and g accounts for the topology derivative, which is accounting for the new hole creation, and omega is the weightage factor. So in the middle term, V accounts for the shape sensitivity, which is also represents the velocity of propagation of the existing holes, and which is multiplied with mod del psi. And during this level set topology optimization, we also need to reinitialize the level set. Reinitialization means bringing back the gradient of level set function to 1 again. So initially it will be 1, gradient will be 1, but as you evolve it, the gradient will fall down from the value of 1. It will become slant or steep. So but at some frequent intervals you need to reinitialize, you need to bring back the gradient to 1 in order to crisply capture the boundaries of the shape. That is done by solving Akinol equation, which is dou psi by dou t plus omega times del psi equal to s of psi naught, where s is the smoothed sine function. So this Akinol equation as well as Hamilton-Jacobi equation are both hyperbolic equations. So they are solved by upwind methods. And for reinitialization, you need to do time marching. Typically, if you time march for about 30 time steps or 25 time steps, that is sufficient enough to bring the gradient back to 1. So coming to the procedure, first we need to mesh the domain, and then we need to initialize the level set function in the domain. Typically, we consider signed distance function as the level set function, and that has to be initialized within the domain. So you can distribute 4 level set functions or 4 circles in a row within the computational domain. And then you need to map the physical properties with the level set function. So here you can assume, say, psi is the level set function, and then psi greater than 0 represents void, and psi less than 0 represents material. So like that, you can assign the material properties based on the value of level set function. Then solve the physics of the problem based on current level set function distribution and the mapping. And then the next step is calculate the shape sensitivity and topology sensitivity. Once you solve the problem, from the problem solution, you can find out the shape sensitivity and topology sensitivity. And then the next step is evolve the level set function to a new shape, so which is done by solving the Hamilton-Jacobi equation. So you know the shape sensitivity, that you substitute that, and then when you solve it, you get the new shape for the level set function. And now you compare the new shape and the new objective with the earlier objective function. So if the change in the objective value is less than some threshold value, then you can assume the solution is converged or optimization is converged, and you can stop it. And if you observe a significant difference, then you need to solve the physics again for that new level set function. So and this loop has to be continued till you get the converged shape and you find no difference in the objective value. So while executing this loop, maybe for every 5 loops or every 6 loops, you can reinitialize the level set functions. So that will bring back the gradient to 1 and ensure you have crisp material boundaries during the level set evolutions. So this is the procedure for level set topology optimization. We'll take one example, cantilever beam problem. So which is fixed at the left hand side, and on the right you have downward load at the center of the right hand side edge. So here the governing equation is Ku equal to F, where K is the stiffness and U is the deflection vector and F is the force vector. So for this cantilever, we have considered a width of domain width of 2 and height of 1, and the domain is discretized by 80 by 40 cells. And so for the volume constraint, we assumed 50% of the material, and the Lagrangian multiplier for that is 100, and iteration 100 iterations are carried out initially. And in this problem, we did not consider new hole creation. That means topology derivative is not used for creating the new holes. So only the existing shape is evolved, existing level set functions are evolved to get the final optimized shape. And this implementation is based on um, Michael Y. Wang's paper on level set based topology optimization. Okay, so here, so the level sets are distributed in this way, and psi greater than 0 is considered as void, and psi less than 0 is considered as material. And psi equal to 0 is represented with this green colored material, and as you run this, you see the level set function evolves, and merge, and now reinitialization is done, and now you get the gradient back to 1, and so now you get the final shape, which is the optimum shape for the cantilever beam with the tip load at the right hand side. Thank you.